So, in this lecture, we will define what is a subspace topology. So, recall that we want to construct a huge collection of topological spaces, and after this discussion, we would have succeeded in that partially. So, from now on, we shall use the phrase a topological space to mean that X is a set with a topology tau on it. So let X be a topological space and let Y contained in X be a subset. Then we can put a topology on Y as follows. Let the topology on X be denoted tau. So we define a subset tau sub Y inside the power set of Y by tau sub Y is U intersection Y, where U belongs to tau. So given an element of tau, we just intersected with Y, and that's how we define the topology in Y. Here's an exercise, which is quite easy. Check that tau sub Y satisfies the three conditions for being a topology on Y. So this topology is called the subspace topology on Y. So here are some simple examples. Let X have the trivial topology that is tau is just the empty set and the whole set X. Then tau Y is the trivial topology. On Y. Example 2 is let X have the discrete topology that is tau is equal to entire power set, then tau y is the discrete topology on y. So 3, the third example is also easy. Let x be the real line with the standard topology with the standard topology, and let y be equal to z, the set of integers. So then the subspace topology on z is is exactly equal to the discrete topology. So to check this, it suffices to show that singletons inside Z are open in the subspace topology, because once we show this, given any subset W inside Z, we will have that we can write W as union n belongs to W, these singleton n's, and as arbitrary unions of open sets are open. This will imply that W is open in Z, which is precisely the meaning of saying that the subspace topology is a discrete topology, because yeah, the discrete topology is exactly that topology in which every set is open. So for this, to check that the singletons are open, let U contained in R be the subset n minus half comma n plus half. So this is an open subset in the standard topology, and when we take U intersection Z, we get exactly n. I mean, yeah, note that U intersection Z is equal to n. So this shows that Z has the discrete topology. Or this shows that the subspace topology in Z is equal to the discrete topology. Equals the discrete topology. So let us consider a slightly more complicated example. Actually, yeah, so let us consider a slightly more complicated example. So let X be R2 with the standard topology. So consider the inclusion map I from R to R2. This is x, we send it to x comma 0. So this is, so we take the real line and we embed it into the plane as the x-axis. So it is 0, so it is 0. So we take an x here and it maps to x comma 0. So let tau denote the standard topology on x, and let S denote the standard topology on R. So using the inclusion, so x, recall here is R2. So using the inclusion I, we can put the subspace topology on R, and let us denote this by tau sub y, and recall that tau sub y is defined as follows. So tau sub y, sorry, so tau sub y is equal to I inverse u, which is equal to u intersection r for every u in tau, and tau is the standard topology on R2. So basically, we have R2. We are taking any open set. So yeah, well, an open set could be more complicated than this. So we can take any open set. And we are just intersecting the open set with R, and the resulting sets are the ones which are going to be open for the topology tau y. So the aim of this example is to show that the standard topology on R is equal to the subspace topology tau y. So we will first prove two lemmas which will enable us to understand the proof more clearly. So the first lemma is as follows. So let x be a set, and suppose tau 1 and tau 2 are two topologies on x. So let B1 contain tau 1 be a basis, for tau 1. So if B1 is contained in tau 2, then tau 1 is contained in tau 2. So the proof is easy. So let U be a subset of X, which is open in tau 1. So we will show that U is open in tau 2. So since B1 is a basis for tau 1, it follows that for every X in U, there is a W sub X in B1 such that X is in W sub X and W sub X is contained in U. Thus, we may write U equal to union X in U, W sub X. Now, since B1 is contained in tau 2, each W sub X, which is a member of B1, is open in tau 2. And as tau 2 is a topology, it contains arbitrary unions of its members. And so, U, which is a union, this is also in tau 2. So this shows that tau 1 is contained in tau 2. So this completes the proof of the lemma. And as a corollary, we get let X be a set, let tau 1 be a topology on X with basis B1, let tau 2 be a topology on X with basis B2 if B1 is contained in tau 2 and B2 is contained in tau 1, then tau 1 is equal to tau 2. So we will use this corollary to prove that the standard topology on the real line is equal to the subspace topology on the real line coming from viewing the real line embedded inside R2 as the x-axis. Okay, but before that we need one more lemma, which is easy and is left. The proof of this is left as an exercise. Let X be a set with a topology tau. Let B be a basis for tau. Let y contained in X be a subset, and let tau sub y denote the subspace topology on Y. Then B sub Y is the union, which is the definition of B sub Y. We are defining a set B sub Y. This U intersection Y for all U in B is a basis for tau sub Y. And the proof is easy and is left as an exercise. So now we will finally prove what we stated. Let S and tau sub y be as described above. Before, then S is equal to tau sub y. So proof. So recall that tau was the standard topology on R2. Let B denote the collection of sets S epsilon AB. This is a square of epsilon 2 epsilon are centered at the point AB. And we saw that B, we have already seen that B is a basis for the standard topology on R2. So let tau sub y denote the subspace topology on R embedded in R2 as the x-axis. So this tau sub y we have defined above. And let B sub y denote the basis for tau sub y obtained as P sub y is equal to U intersection y where U belongs to B. So the previous lemma shows that P sub y is a basis for tau sub y. So let S denote, S is the standard topology on R2. On R, sorry. And let C prime be the collection of these intervals, epsilon balls around X, union the empty set. Then, so let's just call it C instead of C prime. Then C is a basis for S. So we claim that C is equal to By. So to see this, note that for any S epsilon A comma B in B, so what does its intersection with the x-axis look like? So there are two cases. First is that the S epsilon is something like this. In this case, its intersection with the x-axis is 0. And the second case is, it looks something like this. I mean, in the first case, the intersection with the x-axis is the empty set. So we have, so we have either S epsilon a comma b intersection y is the x-axis, is empty, or S epsilon a comma b intersected y is b epsilon, the epsilon ball around a. So this shows that b sub y is contained inside C, and conversely, given b epsilon a in C, we have S epsilon a comma 0 intersected y is exactly b epsilon a. So this shows that C is contained in b sub y. So this proves that C is equal to b sub y. And now applying the previous corollary, we see that S is equal to tau sub y. So this is nice because we have two naturally defined topologies on the same subset, and both of them coincide. So we will end this lecture here.